But for this, sinc function interpolation, right, this perfect interpolation, each value is actually interpolated by infinite number of samples. Right, so this we talked about. So this we also just talked about. So this is basically just summarizing this linear interpolation, which we also call first order Hode. Okay. So this is basically, interpolating by a filter that has a triangular impulse response. Okay. So if you move this to each one of these samples, right, you construct a single x sub r of t that looks like this. Okay. Now in the frequency domain, right, if you take the Fourier transform of this, a triangle in the time domain can be viewed as the convolution of two rectangles. Okay. So the convolution of two rectangles in time corresponds to the multiplication of two sinc functions. Okay. So you can see that using this linear interpolation in the frequency domain, you have a frequency response that looks like this. So if you impose this frequency response on top of your signal, then you're again distorting your signal. Okay? So you either have to apply another filter to compensate for this distortion, or you just try to sample fast enough so that this linear interpolation is a good enough approximation. Okay? So all of this discussion is conditioned on the fact that the sampling theorem is satisfied. Right? You're sampling at a frequency that is greater than twice the bandwidth of your signal. Okay? So all of this is possible only if your sampling frequency, omega s, is greater than twice the bandwidth, omega m. Okay. Now, if this is not true, then x sub p of t will have a spectrum that have overlapping between adjacent replicas. Okay. So if this is not true, then you will get a spectrum like this where you have overlapping between adjacent spectrums. And this is what we call aliasing. Okay? So aliasing basically messes up the signal. Okay? So to gain some insight on what aliasing may do to your signal, right, we can look at a very simple case of a sinusoid. Okay. So here we want to look at the effect of aliasing, right, looking at a very simple sinusoid. Let's say x of t equal to cosine omega naught t. Okay. So by Euler's relation, this can be written as 1/2 e to the j omega naught t plus e to the minus j omega naught t. Okay? So in the frequency domain, this is just two impulses at frequency omega naught and minus omega naught. Okay? So this is the Fourier transform of x of t. Right? This is the Fourier transform of x of t. I have an impulse delta function at omega naught and a delta function at minus omega naught. Okay. Now suppose I sample this sinusoid fast enough. So suppose I choose a omega s that is greater than 2 times omega naught. Okay? So when I sample, I will get x sub p that have a spectrum repeated every integer multiple of omega s. Okay? So if omega s is large enough, then there is clear separation between adjacent replicas. Okay? So when there is clear separation, when there is clear separation, then you can reconstruct the original sinusoid by just imposing a low-pass filter on top of xp. Okay. All right. Now, suppose that omega naught is larger, right? So suppose that the bandwidth is a little bit larger, right? This sinusoid oscillates faster, right? So the bandwidth increases. But as long as omega naught is less than omega s over 2, it's okay, right? We can still reconstruct it with this filter. But if we increase omega naught further, right? If we increase it beyond omega s over 2, what happens? Originally, it's here, but now it moves here. And the replica on this side moves here. Okay? So this is moved here. This is moved here. Okay? And these things on the side are moved into the range of the low-pass filter. Okay? So now when you impose a low-pass filter on this signal xp of t, what do you get? Right. You no longer get a sinusoid of frequency omega naught. Instead, now you get a sinusoid with frequency omega s minus omega naught. Okay? So this gives you right, if you filter this out, this gives you a sinusoid at frequency omega s minus omega naught. Okay? So you get a sinusoid that is at a completely different frequency. Okay? And this is the same if you just, if you increase it even further. Right? So this is increasing even further. So, actually, so for example, if you compare this case with its original spectrum, right? So originally, omega naught is actually at a very high frequency, right? So originally, omega naught is at a very high frequency, meaning that you have a sinusoid that oscillates really fast. But actually, when you low-pass filter it, if you low-pass filter the sample, you will actually get a sinusoid that actually varies very slowly. Okay? So even though the original is very fast, after sampling and recovery, you actually get something that is very slow. Okay? Right. So there are the corresponding figures are given in the following. Okay? So this is the original sinusoid. This is the original sinusoid. And right, if omega naught is omega s over 6, right, such as this case here, okay? So if omega naught is much smaller than omega s over 2, or omega s over 6 to be exact, then taking these samples, you can recover the original sinusoid perfectly. Okay? Now, you can increase the frequency of the sinusoid slightly to, let's say, 2 omega s over 6. Now, this is still smaller than omega s over 2, right? This is still smaller than omega s over 2. Okay? So after low-pass filtering, you can again get back this same sinusoid. But now, if you increase omega naught further, okay, so suppose you increase omega naught to 4 omega s over 6, which is greater than omega s over 2. Okay. Then what happens? Okay. So originally, your sinusoid should be, really at a really high frequency, right? So originally, your omega naught is at a very high frequency, but after sampling and low-pass filtering, you actually get back a sinusoid at a much lower frequency. Okay. So even though originally it's at a high frequency, so this is at frequency omega naught, the reconstructed signal is actually at frequency omega s minus omega naught. Okay? And the same here, right? So even though the original signal is at high frequency, your reconstructed one is at a very low frequency. So this is also the cause of what we call the stroboscopic effect. Okay, so let me skip over this example for now. Okay, and look at this. Okay, so this is also the reasoning behind what you call a stroboscopic effect. Okay, so what is a stroboscopic effect? If you've ever watched a movie, right, where you see this vehicle passing through, and the wheel, right, actually seems to turn backwards, even though it's going at a very high speed, right? I don't know if you've ever experienced this, but when you watch certain movies, right, like you have these race cars, running down the street, right, at a very high speed, but actually you see the wheels turning backward, right? So this is actually caused by aliasing, okay? So for example, suppose you have this wheel turning at this speed here. So if you sample fast enough, right, you can see this going forward, right? So this is because we're sampling fast enough, okay? And our visual system serves as a low-pass filter that sort of recovers this oscillation, okay? But, if you do not sample fast enough, all right, what do you see? Right? You see it going backwards, right? Okay. So this is the effect of aliasing, okay? All right. Okay, so again, Nyquist sampling tells us that if you want to recover the original signal, you need to sample at a rate that is greater than twice the bandwidth of your signal. Okay. So in this example here, we're trying to see what happens if you sample at exactly twice the bandwidth. Okay, so previously we sort of emphasized the fact that it should be strictly greater. So we emphasize the fact that it should be strictly greater, right? Now what happens if it is exactly equal, okay? So for most cases, it probably does not have such much of an effect, but in certain cases, it could cause some trouble, okay? And this is an example of when, you may see trouble by sampling at exactly twice its frequency. Okay. So the thing is that suppose you consider a signal x of t equal to cosine omega s over 2t plus phi. Okay. So you can actually write this as, okay, so this signal has frequency omega s over 2. Okay. Now this signal you can write as cosine omega s over 2t times times cosine phi minus sine omega s over 2t times sine phi. Okay? So you get this by trigonometric identity, right? Cosine A plus B gives you cosine A times cosine B minus sine A times sine B. Okay. So the thing is that if you sample at exactly, at exactly twice the bandwidth, so this means that, right? This means that you're sampling at points t. So sampled at twice its frequency means that you're sampling at t equal to 0 plus and minus 2 pi over omega s plus and minus 2 times 2 pi over omega s, and so on and so forth. Okay? So sampling at twice the frequency means that you're sampling at, at a period equal to 2 pi over omega s. Okay? So the sampling frequency is omega s, which is exactly twice of omega s over 2. Okay? So if you do that, right, if you substitute this inside, you will see that this second term of sine is always 0. Okay? So this term is always 0 at the sampling points. So always 0 at the sampling time. Okay? So by sampling at these points, you actually get only this signal here. So when you recover, the recovered signal will contain only this and not this. Okay? Right. So this is an extreme example, right? This is an extreme example because x of t equal to sine omega s over 2t is actually equal to cosine omega s over 2t plus a phase that is minus pi over 2. Okay? So this is actually equal to cosine omega s over 2 t plus phi that is minus pi over 2. Okay. And in this case, if you sample at these points, you're actually sampling at all these 0 points. Okay? So when you recover the signal, you'll probably just recover a straight 0 signal instead of a sinusoid. Okay? So this is just an example to show you that sometimes when you're sampling at exactly twice the bandwidth, you may have some trouble when these boundary points, overlap with each other. Okay. But actually, in practice, you never want to choose, you never want to choose omega s that is so close to twice the bandwidth. Okay. So in practice, in practice, you would not want to choose omega s so close to 2 times omega m. You always need to give sufficient separation between adjacent replicas because in practice, we can never have an ideal low-pass filter. So practical filters always need some time to transition from pass band to stop band. So you always need a sufficient separation for that to happen, okay? But theoretically, this is possible, okay? All right, so I can maybe stop here for today. Okay, but maybe just to sort of preview what we talk about next week. So this is the motivation for converting continuous time signals to discrete time, okay? So suppose this is a continuous time signal. We want to convert it to discrete time signal so that we can process this in discrete time. And this DSP system is usually more efficiently done in the digital domain, right? So we have all these digital circuits that have very high efficiency. So we prefer to operate things in discrete time in the digital domain rather than in continuous time. But once we are done, we can always reconstruct the continuous time signal using all these different interpolation schemes, okay? So we'll talk about this next time.